we're used to the fact that people who can manipulate language very well are implicitly smart. But we're being fooled. You can't really use this technique to build intelligent
these AIs conscious?
Absolutely not.
Adam?
Probably not.
Okay. Will they soon be?
I think they'll one day be conscious if progress continues in the way that we're continuing. When is hard to say, but one day.
Mm-hmm.
Yes, for appropriate definitions of consciousness.
Yes. Okay. Well, we do have some philosophers in the house, and we're not going to indulge in philosophical definitions of consciousness, or our hour would go, and we'd still be here. Oh, I just heard that groan, I think, from our friends up in the balcony. Yes. But I have one other question. Okay, no, I have two. I have two in the lightning round. Are we on the precipice of doomsday or a renaissance in human creativity? Yann?
Renaissance.
Adam?
Most likely Renaissance.
I have to throw this out. The same question to the audience, but I'm going to phrase it more colorfully, which I think they'll relate to. Will the robot overlords rise up against humanity? Yes, hands up. Oh, interesting. Okay, no, hands up. Okay, how many robots in the audience? Hands up. Okay, so that's interesting. See, that's cool. It was a little more no's, maybe, although the light is blinding. All right, we're going to come back and ask that again at the end. So here we are. These neural nets have been taught to execute a process we now call deep learning, and there's other kinds of learning that take off. And what are the large language models specifically, which is really what has swept up the news and people's personal experience? We're mostly relating to large language models. And what are the large language models, Adam? Maybe you could take that.
Yeah, so a large language model is, you've probably played with some of them, ChatGPT, Gemini, made by my company, various others made by other companies. It is a special kind of neural network that's trained on particular inputs and particular outputs and trained in a particular way. So it is, at heart, it is mainly the kind of deep neural network that was pioneered by Yann and by others, but with a particular architecture designed for the following task. It takes text in, so it'll read the first few words of some sentence or the first few paragraphs of some book, and it will try and predict what the next word is going to be. And so you take a deep neural network with a particular architecture, and you have it read, basically, to first approximation, the entire internet. And for every word that comes along on the entire internet, all of the text data and now other kind of data you can find, you then ask it, what do you think the next word's going to be? What do you think the next word's going to be? And to the extent that it gets it right, you give it a little bit of reward and strengthen those neural pathways. To the extent that it gets it wrong, you diminish those neural pathways. And if you do that, it'll just start off spewing just completely random words for its prediction. But if you train it on 1 million words, it'll still be spewing random words. If you train it on a billion words, it'll maybe have just started to learn subject, verb, object, and various bits of sentence structure. And if you train it, as we do today, on 1 trillion words or more, tens of trillions of words, then it'll start become the conversation partner that you probably, I hope, played around with today.
Now, it strikes me as intriguing. Like it amuses me sometimes. People get really outraged at their chatbot that they're engaged with when it leads them astray or lies to them. And sometimes I've said, well, it doesn't need to be words. It might as well be colors or symbols. It's just playing a mathematical game, and therefore doesn't have a sense of meaning. Now, I know Adam sort of objected to my summary of that. Do you think that they are extracting meaning in the same sense that we do when we are engaging in composing sentences?
Well, they're certainly extracting some meaning, but it's a lot more superficial than what most humans would extract from text. Most humans intelligence is linked to, is grounded into an underlying reality, right? And language is a way to express phenomena or things in that, or concepts grounded in that reality. LLMs don't have any notion of the underlying reality. And so their understanding is relatively superficial. They don't really have common sense in the way that we understand it. But if you train them long enough, they will answer correctly most questions that people will think about asking. That's the way they're trained. You collect all the questions that everybody has ever asked them, and then you train them to produce the correct answer for this. Now, there's always going to be new questions or new prompts, new sequences of words for which the system has not really been trained and for which it might produce complete nonsense. Okay, so in that sense, they don't have the real understanding of the underlying reality, or they do have an understanding, but it's superficial. And so, the next question is, how do we fix that?
So I could play devil's advocate and say, well, how do I know that what a human being is doing is that much different, right? We're trained on lots of language. We get some dopamine hit or some reward system for having said the right word at the right time and the right grammatical structure for the language that we're immersed in. And we backpropagate. We try to do a better job the next time. In some sense, how is that different than what a human being is doing? And you were saying maybe it's the sensory experience of being immersed in the world?
Okay. A typical LLM, as I mentioned, is trained on tens of trillions of words. Typically,
there's only a few 100,000 words. You're just saying sentences. It's combinations.
No, it's 30 trillion words is a typical size for the training set, pre-training of an LLM. A word is represented actually as sequences of tokens, doesn't really matter. And a token is about 3 bytes, so the total is about 10 to the 14 bytes, right? One with 14 zeros of training data to train those LLMs. And that corresponds to basically all the text that is publicly available on the internet, plus some other stuff. And it would take any of us something like half a million years for any of us to read through that material, right? So it's an enormous amount of textual data. Now compare this with what a child perceives during the first few years of life. Psychologists tell us that a 4-year-old has been awake a total of 16,000 hours. And there's about 1 byte per second going through the optic nerve, every single fiber of the optic nerve, and we have 2 million of them. So it's about 2 megabytes per second getting to the visual cortex. During 16,000 hours, do the arithmetics, and it's about 10 to the 14 bytes. A 4-year-old has seen as much visual data as the biggest LLM trained on the entire text ever produced. And so what that tells you is that there is way more information in the real world, but it's also much more complicated. It's noisy, it's high-dimensional, it's continuous, and basically the methods that are employed to train LLMs do not work in the real world. That explains why we have LLMs that can pass the bar exam or solve equations or compute integrals like college students and solve math problems. But we still don't have a domestic robot that can, do the chores in the house. We don't even have level 5 self-driving cars. I mean, we have them, but we cheat. So, we certainly don't have self-driving cars that can learn to drive in 20 hours of practice like any teenager, right? So obviously, we're missing something very big to get machines to the level of human or even animal intelligence, right? Let's not talk about language. Let's talk about how a cat is intelligent or a dog. We're not even at that level with AI systems.
Mm-hmm. Adam, you impart more comprehension on the part of the LLMs at this point already.
I think that's right. So, Yann is making sort of excellent points that the LLMs are much less, for example, sample efficient than humans. Humans, or indeed your cat, or just a cat, I don't know if it was your cat or a cat.
He's a very smart cat.
In your example, is able to learn from many fewer examples than a large language model, for example, can learn from, that takes way more data to teach it to the same level of proficiency. And that's true, and that is a thing that is better about the architecture of animal minds compared to these artificial minds that we're building. On the other hand, sample efficiency isn't everything. We see this frequently, in fact, when we try and, before large language models, when we try and put machines on, make artificial minds to do other tasks. Even the famous chess bots that we built on top of large language models, the way they were trained, sort of AlphaZero and various other ones, they would play each other. They would play itself at chess a huge number of times. And to begin with, it would just be making random moves. And then every time it won or lost the game, when it was playing itself, it would sort of reward that neural pathway or punish that neural pathway. And they play each other at chess again and again. And when they played as many games as a human grandmaster has played, they were still making essentially random moves. But they were not confined to making the same number of playing the same number of games that a human grandmaster could play. Because silicon chips are so fast, because we can build them with such parallel processing, they were able to play many more games than any human could ever play in their lifetime. And what we found is that when they did that, they reached and then far surpassed the level of human chess players. They're less sample efficient, but that doesn't mean they're worse at chess. It is clear that they're much better at chess. So too with understanding. When it is true that we can, it is harder with these things you need more samples to get them up to the same level of proficiency. But the question is, once they've reached that, can we use the fact that they are so much more general and so much faster and more inerrant to push beyond that? I mean, another example perhaps with the cat is a cat is in fact even more sample efficient than a human. A human takes a year to learn to walk. A cat learns to walk in a week or so. It's much faster. That does not mean that a cat is smarter than a human. It does not mean that a cat is smarter than a large language model. The final question at the end should be, what is the capabilities of these things? How far can we push the capabilities? And on almost every, except for the somewhat impoverished metric of sample efficiency, on every metric that counts, we've pushed these large language models far beyond the frontier of cat intelligence.
Now, Adam, I know that you are less pessimistic about the potential of the current neural net deep learning paradigm, and you see the potential for a great escalation in success, and you don't see it saturating. What's your thought about that?
I don't. That's right.
And so, yeah.
We have witnessed over the last 5 years the most extraordinary run-up in capabilities in any system I've ever seen. This is what transfixed my attention. It's what transfixed many other people in AI and neighboring fields to focus all of our attention on this matter. I don't see any slowdown in the capabilities. A year ago, if you just look at all of the metrics we use to judge how good these large language models are, they're getting stronger and stronger and stronger. Things that the model from a year ago today would be, table stakes, would be considered extremely poor. Every few months, these things push their capabilities. And if you track their capabilities on all of these tasks, they're heading towards superhuman on almost all of them. It's already gives better legal advice than a lawyer. It gives better, it's a better poet than almost every poet you will come. In my little area of physics, I use it because there's something I kind of should know, but I don't. I'll ask the language model, and it will not only tell me what the right answer is, it will patiently and I should say non-judgmentally listen while I explain my misconception to it, and it will carefully debunk my misconception. The extraordinary run-up in capabilities that we've seen over the last 5 years, and that continues up to the present, is extremely tantalizing to me and many other people in San Francisco. And maybe Yann is correct that we're just going to suddenly saturate, and all of these straight lines that have been going up steadily for the last 5 years are suddenly going to stop going up. But I am mighty curious to see whether we can push it further. And I've actually seen no indication whatsoever that it's slowing down. Every indication I've seen is that these are improving. And we don't have far to go, because once it's a better coder than almost all our best coders, it can start improving itself. And then we're really in for a wild ride.
Well, we've had better coders than the original coders of the 1950s, for 6 decades or so. That's called compilers. I mean, we keep getting confused about the fact that it's not because machines are good at a certain number of tasks that they have all the underlying intelligence that we assume a human having those capabilities will have, right? We're fooled into thinking those machines are intelligent because they can manipulate language. And we're used to the fact that people who can manipulate language very well are implicitly smart. But we're being fooled. Now, they're useful. There's no question. We can use them to do what you said. I use them for similar things. Great. They're great tools, like computers have been for the last 5 decades. But let me make an interesting historical point. And this is maybe due to my age. There's been generation after generation of AI scientists since the 1950s claiming that the technique that they just discovered was going to be the ticket for human-level intelligence. You see declarations of Marvin Minsky, Newell and Simon, Frank Rosenblatt, who invented the perceptron, the first learning machine in the 1950s, saying, like, within 10 years, we'll have machines that are as smart as humans. They were all wrong. This generation with LLM is also wrong. I've seen 3 of those generations in my lifetime, okay? So, it's just another example of being fooled. And in the 50s, Newell and Simon, pioneers of AI, came up with a program that said, well, really what humans are doing is in reasoning is really a search, right? Every reasoning can be reduced to kind of a kind of search. So you formulate a problem, you write a program that tells you whether a particular proposal for a solution is a solution to your problem, and then you just have to search for all possible combinations, all possible hypotheses for one that actually matches, satisfies the constraint. And that's it. We're going to write a program that does this, and we're going to call it the General Problem Solver, GPS, 1950. 7, I think. They won the Turing Award for things like that, and it was great. But then they didn't realize that all the interesting problems actually have a complexity that grows exponentially with the size of the problem. So in fact, you can't really use this technique to build intelligent machines. It can be a component of it, but it's really not the thing. Simultaneously, Frank Rosenblatt came up with a perceptron, a machine that could learn. And he said, if we can train a machine, then it can become infinitely smart. And so within 10 years, we just need to build bigger perceptrons, right? Not realizing that you need to train multiple layers, and that turned out to be difficult to find a solution for this. Then in the 1980s, there was expert systems. Okay. Reasoning is fine. Just write a bunch of facts and a bunch of rules, and then just deduce all the facts from the original facts and the rules. And now we can reduce all the human knowledge into this. The coolest job is going to be knowledge engineer. You're going to sit down next to an expert and then write down all the rules and the facts and turn this into an expert system. And everybody was excited about this, and there were billions that were invested. Japan started the 5th generation computer project, which was going to revolutionize computer science. Complete failure. Okay, it created an industry. It was useful for a few things, but basically the cost of reducing human knowledge to rules was just too high for most problems, and so the whole thing collapsed. Then there was neural nets, the second wave of neural nets in the 1980s, which we now call deep learning. A lot of interest, but then it was before the internet. We didn't have enough data. We didn't have powerful computers. And now we're going through the same cycle again, and we're getting fooled again.
Just one closing question. We're a little bit over time, but I'm going to ask this to you, Yann. In many ways, you're a contrarian, maybe not by choice. Maybe this is just how it's happened. You've called it the cult of LLMs. You sort of often refer to the fact that in Silicon Valley, you don't have the most conventional approach. But yet, you have an optimism. You really do not indulge in the doomsday sort of rhetoric. What is your most optimistic vision for, if not 2 years from now, 2036?
Well, the new renaissance, that's a pretty optimistic view of, AI systems that amplify human intelligence, is under our control, can solve a lot of complex problems, can accelerate the progress of science and medicine, can educate our children, help us, process all the information or bring us all the knowledge and information that we need to see. In fact, people have been interacting with AI systems for much longer than they realize. Of course, there is, LLMs and chatbots now for the last 3 years. But before that, like every car sold in the EU and most cars sold in the US have what's called ADAS, Advanced Driving Assistance Systems, or automatic emergency braking systems. A camera that looks out the window and stops your car if you're about to hit a pedestrian or another car. It saves lives. You get an X-ray today, let's say a mammogram or something. At the bottom it says the thing has been reviewed by an AI system. It saves lives. You can get an MRI now, full body MRI in 40 minutes. This is because you can accelerate the process of collecting the data because AI systems can sort of fill in the blanks. You don't need to collect as much data for this. But also all the news you're seeing, whether you connect on Google or Facebook, Instagram, any social network, is determined by an AI system that basically caters to your interests. And so, AI has been with us for a while already.
But you're saying we should be impressed when they can pour a glass of water and do our dishes.
Pour a glass of water, do our dishes, drive our cars, learn to drive our cars in 10 hours.
Without the cheating,
practice,
yes.
Without all the cheating with sensors and mapping and hard coding of rules. So, this is going to take a while. But this is going to be the next revolution of AI. So this is what I'm working on, okay? And the message I've been, carrying for a while now is okay, LLMs are great, they're useful, we should invest in them. A lot of people are going to use them. They are not a path to human-level intelligence. They're just not. Right now, they're sucking the air out of the room anywhere they go. And so there's basically no resource left for anything else. And so for the next revolution, we need to kind of, take a step back and figure out what's missing from current approaches. And then I've been making proposals on this and working inside of Meta for a number of years on this alternative approach. It's come to the point where we need to kind of accelerate this progress now because we know it works. We have early results, and so that's the plan.
Okay, we could have a whole another hour starting right here, but I hope you'll all join me in thanking our guests for an incredible conversation. Thank you so much.
We don't play that. We don't play that. We don't play that. G-Unit. We don't play around.